surreal to see that video. And I think validity overall has been a major focus, particularly since I think it used to be a bigger customer question when people were getting to know us. And it's an industry where it's uniquely, a lot of people say, well, where's your white paper validation study, when you show them the device. So that, how do you ensure a device is accurate? Well, you need to have a whole bunch of quality checks. So internally, all the plastics we make get measured down to the fraction of a millimeter, and every little flow tube can't change. And when you put a device together, you have to do a leak check. All the tubes you connect, they can't leak a microliter. And they have to all flow the same, so you can do a flow through test. When the unit's fully assembled, it goes on a lung simulator, one of the 4 lung simulators we have, 3 we bought, 1 we built. And you do a set point check saying, will this thing actually produce the required data across the full measurement range? And every single unit produced gets 2 of those checks, gets a calibration certificate before it gets shipped, and the people who made it, 2 of them have to sign off that they really think this thing works. And we use similar quality checks in research and development. But essentially, we have 3 more standard simulators that do everything from resting metabolics all the way up to, national level athlete breathing, fast, shallow breathing, slow, deep. And then we built a lung simulator that does heat and humidity. It's based off the GESS simulator from the University of Cologne. And essentially, what do the engineers spend a big part of the time trying to do is trying to break the device. And in doing that for years, you make it very robust. You try to you say, okay, it can last for hours and hours on a person's face. Well, let's make the room cold and make the exhale there super hot and super humid and try to break it. Okay, we broke it. Good. Let's make it better and better and better and better.
I guess it's what you would do with a theory that you're trying to invalidate. You just got to chip away at whatever you can until last man standing kind of thing. And I guess that's the true process of the scientific method, if you will, or one of its components, in a very applied sense, I guess. But like you said, try to break it. If it doesn't break, good. If it does, let's fix it and keep moving forward.
And you'll always have some, I don't mean to speak about it negatively, it's more my engineering side of my brain of you'll always be able to break a device. No device works all the time for everything. So you try to build it out to, the first product you release is good for 80% of people out there. And then, after a few years, you're good for 99.9% of all use cases. Does it still work when it's freezing cold out? No, but it works just about every other time. So
that's a fascinating thing, because some of our original prototypes I was taking up and working with some cross-country skiers up on the snow, and the device would actually ice up because one day we took it up, it was bucketing deep, heavy snow, and she was one of our national team athletes, and it froze and has this big long icicle coming off of it just from the humidified air that she was blowing out. And Peter said, the data is not going to be accurate from that test, right? It's changed the shape of the venturi, the pressures are going to be off. And I said to him, yeah, but we tested a cross-country skier, and I was able to actually show her respiratory frequency and her tidal volumes. And even if we say the tidal volumes are off, I can see how fast she was breathing, and I can see how she changed on her multiple laps. And I could use that as a coaching tool now for her to shift. So we went back out right afterwards, and as she would skate by, her coach was looking at the thing. He goes, that totally worked. That breathing pattern has totally worked. And I go, how do you know? And he said, look at the way she's skiing. And I'm like, okay. And he said, I can't believe that we were able to have a device that showed me how she's breathing, because I could tell how she skied from watching her from the bottom of the hill, but I could never see how she breathed. And now we could see her breathing and her technique at the same time. So even though the device has flaws in temperature, the data that we were pulling was still so valuable for the coach and the athlete that it completely changed it changed her technique and her tactics for racing on a hilly course. And that's what I keep, it's the argument that Peter and I keep getting back to, because Peter goes, it's not, I want to make it more accurate. I want to fix these little things. I said, Peter, you're not understanding how good this thing is already. Like it's so good. We need to, and this is from 3 years ago, we said, we need to get it into people's hands because they're going to be blown away with the data that they're getting. Even if at the time we could say, yeah, it's not accurate if it gets too cold. It's not accurate if it gets humid. And there are limitations to our device in extreme temperatures and heavy winds or super humid or other things. And that's a device. But the difference is we can take our device. The difference is we could take our device to the hill.
Right.
Yeah, like if you want the most decimal points in your data table, I mean, you can go to a lab and use a lab cart. You can sit on a treadmill or a bike. And if you don't ride a bike or run on a treadmill, if you don't ride a stationary bike or run on a treadmill, it's not going to be completely applicable to your sport. I mean, that's, you know, you need actionable data in situ in the sport you're testing. I think you need to do that repetitively to see change, relative change. Did the training you prescribed based on the objective insight actually work and remove their limiter? And Andrew might correct me on this, but the way I often explain it is like, so you happen to have an athlete that's plateaued for a year or two, and they happen to do a ton of long, slow training, and they're working on mitochondrial density and cardiac function, but they never work on their own breathing. And you do a step test with them and you realize they can't coordinate deep breathing at all. You know, no matter how much stronger and bigger they make their heart, they can't go faster. You have to address their limiter. Teach them to breathe better. You might actually be able to reduce the training they're doing just to address that limiter and watch them get better. And then you retest and you say, yeah, you could actually coordinate deeper breathing at higher intensities. And look, you just got 15% better because your heart can actually be used.
Yeah, that was kind of that was one of the first things that came up for me once I started just even realizing that respiratory training was a thing. And that then, you know, I found your guys's work simply by trying to find a way to sync my Moxie data together. And like, I guess that goes back to Peter's early work of making one big, nice, clean CSV for everybody to work with. And that's pretty much what I get out of it. Now, obviously Moxie is working on their portal and that's gonna be great for all Moxie users. But I mean, just being able to bring all that data together, and then, like you said, understanding that, hey, those values that we're measuring on the respiratory side, this is, like you said, this is applied. This is out on the field. This is either on a bike or running, or like I'm thinking, you know, put it on a rugby player and do some intervals and see how they react. But like you said, they're numbers that you can then actionably use in training and retest and actually see some changes. And the fundamental importance of respiratory frequency, tidal volumes, and understanding how those are being modulated throughout an effort, given the person's basic capabilities of lung volume and FEV and stuff like that. This is such a valuable tool to add to any coach's toolkit who just wants to, it's not even go that step farther. Now I feel like respiratory training is wholly underappreciated amongst coaches. I feel like it should be a part of training, just like strength training is a part of training. But I think there's still a lot of unknowns, or from people who don't know about it. And the first time I heard about respiratory training, I was like, how does this work? This is a completely new concept. I don't understand. And now it's it's like, you know, the basic principles of strength and conditioning that you would apply: specificity and progressive overload and individuality and adaptation. All those things apply just the same, because respiratory muscles are muscles and they train like muscles. They have ranges of motion, they contract and they relax. And if you're able to coordinate them better, then you're actually going to get somewhere with it, right?
Yeah, you are absolutely right about the public perception of breathing and the shift that is happening. It happened, the shift in high performance athletics happened 15 years ago, but it was so effective for those top end athletes that they didn't want to tell anybody else, because it was an advantage. And you can see this if you actually look at the history of some very successful athletes. And the biggest and the most obvious for some of your listeners would be the Swiss mountain bike team that all began SpiroTiger training, because the SpiroTiger was a Swiss device that was marketed and sold as a performance training device to Swiss athletes first, and they benefited from it because they adopted it early. And when you look at top World Cup mountain bike efforts and you see that there's 5 or 6 guys in the top 10, and you realize that all of those guys were SpiroTiger trained as youth, then it's not surprising. Schurter is a longtime SpiroTiger user, and yeah, it's not a coincidence that he has made that a part of his program. And then when you look at the original research that was done and you follow the paths of the PhD students that were involved in that original research and the impact they have had when they went back to their original home. So one of them is, so Boutillier is one of the original researchers, had his hands on some high performance athletes who he had effects on. And then his PhD student was Christina Spengler. She went back to Britain, took the respiratory training with her to the British rowing team. That team happened to be won a bunch of gold medals for the first time and became a dominant powerhouse. Now, I don't know if they're still doing SpiroTiger training or respiratory training. They're still a world powerhouse, but it'd be interesting if when she stopped doing that work and they moved away from it, if you actually look at the results coming down. And until they get someone, I don't know if it was on your podcast or someone else, said that the increasing the changes in training happen out of necessity. So when you're no longer able to be competitive against the people, you're not able to beat the best people in the world, then something necessitates a change in how you train. So nobody is going to beat Schurter until they start training differently and up to his standards. If they're not doing the minimum to change their systems, they're never going to beat him. And yes, he'll lose races occasionally, but he is still by far and away the top mountain bike athlete in the world. And someone's going to have to realize that he's done things that other athletes haven't done. And one of that is respiratory training. And so if you want to compete at the world level, you're going to have to focus on your breathing, because all the other things have been maximized. Rowers have done weights in a gym since the beginning of time. And you can modify strength training in the gym to a high level. And Moxie's helping understand why some of those systems worked for some athletes and why it maybe didn't work for others. And that whole idea that everybody lifts the same amount of weight for the same duration and the same numbers, where one guy reaches his max after 3 reps and the other guy needs to do it 6 or 7 times to get the same effect. You can now do that with Moxie, which is brilliant. The same thing with breathing. You can train everybody at the same speed on a bike or in a group, and one guy is getting perfect training, and the other 10 guys that are following along are not getting the same training as the one guy who's having the perfect training for him. And that really is where the devices and ability to measure stuff, and like you say, the rugby players breathing, how do they breathe when they're doing wind sprints? How do they recover when they stop sprinting? Never been looked at. They've only ever been looked at how fast do they run on a treadmill and what's their VO2 max. Like, who cares? I want to know how they're breathing the whole way up to VO2 max, and what happens when they stop. Do they keep breathing hard? You look at any of the data from the research that's done with VO2 testing, they have eliminated and ignored all of the really interesting data around breathing. And so I really hope that our device is going to help researchers do the work that they should have been doing for the last 50 years, and that's looking at how people breathe during their efforts, not just what their oxygen consumption is. The oxygen consumption is interesting and has a role, but it's much less interesting than the dynamics of breathing, which has such huge, profound impacts across all sports.
Peter, were you going to say something?
Yeah, I think we've almost come full circle. This started as a data analysis challenge, and I think we fixed some of the hardware challenges, and now we're back at this. It's easy enough to prescribe standard VO2 max step tests and resting metabolic tests, and they have value. But I think the next step is how do you go beyond that in turning some of these more modern ideas into a repeatable system? And I think it involves measuring global VO2 and ventilation and tidal volume and breathing dynamics, and measuring several Moxie sensors, and measuring speed, power, or cadence to get the biomechanics side of it, and heart rate to get an insight on the cardiovascular system. And the fusion of all those data streams should give you this kind of application-specific insight. So I think that's sort of the direction we're heading now, and I'm, I think it's really exciting to be able to experiment with all these new ideas, and in conjunction with our customers too. You know, a lot of people that buy our device, man, they know a lot more than I do about physiology. That's for sure. I just, you know, I know more the product side, and it's fascinating to work with them and build out new ideas. I mean, and same with working with Moxie and with users like you, Sean, of, you know, trying to make sure our app does every little thing to collect the data you need and to visualize it. And I hope at some point, you know, that turns into not just collect and visualize data, but actually interpret, make information from the data. You know, because I think that's a budding idea in the community. There's enough Moxie research out there that, you know, we're pretty sure what a 515 test means in viewing it, but right now it's a visual interpretation done by people. And hope one day, you know, our app will be able to do a good part of that automatically.